Welcome. I appreciate you being here. Today we're going to do a few things. Takeaways here today, really want to try and understand what proper welding and finishing requirements look like, the effect of poor welding techniques on hygiene, why does it matter. We're going to look at things like microbial harborage, material failures that can happen. A lot of times we don't really appreciate the idea that something I like to remind people of is that stainless steel is just steel. In fact, metallurgically, it's very, very close to just carbon steel. And there's a few things that we add in there, like moly and nickel and chromium, that make it stainless, but it's highly susceptible to being reverted back to just steel and can rust. So something to be aware of. And then we'll talk about some advanced techniques. There's a lot of things going on here when we talk about proper welding techniques. Probably more going on here when we talk about OSHA violations maybe, but if you ever see anybody doing any sort of welding of, quite frankly, anything, but particularly stainless steel, in any sort of way like this, stop them immediately and ask them to go way, way far away from anything you're going to have anything to do with. That's more of just a joke. Starting off with welding and finishing for tubing. So AWS D18.1 covers welding of tube, pipelines, and things like this. I've been doing this a long time and I've seen a lot of things. I remember walking into a facility in California one time and I noticed a few things. One thing I noticed was they had a MIG welder. Well, that's okay as long as you're welding some structure or something like this. If you know what a MIG welder is, it's a wire feed welder. They also had a chop saw. You know what a chop saw is? It kind of looks like the thing you buy at Home Depot and it's got an abrasive blade on it. Well, as it turns out, they were cutting the tubing with the chop saw, the sanitary tubing. And fortunately, they weren't using the MIG welder for the sanitary tubing, but they were using that as a chop saw. There's reasons we talk about end prep for sanitary tubing. When we're using a TIG welder on sanitary tubing, D18.1 basically doesn't allow for us to use filler materials. And the reason is those ends of that tubing should be perfectly flush and smooth so that when you're doing that fusion weld, you don't need to add in filler material for, say, 316 or 304 stainless steel. We would metallurgically for things like AL6XN, like we talked about yesterday. This is why using proper end prep machines, whether that be a saw like you see here, there are other end prepping machines that are available to prep those ends properly so they fit up and fit nicely and square and there's no light shining between them, there's no inconsistencies there. We want that because otherwise you can't create a good fusion weld with your TIG. The other part of this is alignment. You can see on the top side, we talk about alignment. Misalignment in a tubing creates a lot of issues. One is you can't get a good weld. It's likely you're going to have inconsistency. Sometimes misalignment can be caused by ovality in the tubing. If the tubing's been transported improperly and it actually isn't round anymore, and then when you cut it, you get a little bit of ovality. That's going to cause some misalignment. We allow for 15% of the thickness of the wall in misalignment. That's not a lot. Tube is 065 wall, so you can imagine there's not a lot of misalignment, but 15% is still very noticeable to any good technician who's doing this. So there's really no reason for misalignment. Occasionally when you get in situ welds, it can be more difficult to do it properly, but it can be done properly. Just an example of a poorly done weld. There's a lot going on there. That one happened to have the situation of it was too much heat in the tack weld. We talked about that yesterday some. As we're doing tack welds, we want that weld only to not penetrate all the way through. We want it just to be on the outside surface. If we penetrate all the way through, we have the situation of creating a poor platform for the weld to continue to penetrate as we're doing the full weld. And then as we talked about yesterday as well, this is the D18.2 color chart showing different colorations. I do have people ask, it doesn't seem possible that these are welds that are done without any additional manipulation. Those are not color cleaned afterwards. This is literally a weld as it came off of the welder. 1 and 2 can be very difficult to do, but 3 is what we typically expect and would want to see. As you get up into these other colorations, you start running into issues. We allow it if you remove the color, but you do have situation, particularly if you're running into products that have susceptibility to be high corrosive environments, you're going to, even with the color removed, set yourself up for potential for corrosion because you've disrupted the structure of that metal significantly at the surface level because of the oxygen content that was allowed. This has been done with the machine, has the same setup, but the only thing that was changed was the parts per million of oxygen. So this is shown to show you that your oxygen content at very small levels will affect the coloration because it's oxidizing. But if I took this number 3 weld and I increased the amperage on that welder to try and make it go faster, or I slowed the speed down so it would actually had higher dwell time at that same oxygen content might look like this. And more heat is not good. I mean, there is a good middle ground. AWS covers that, I think, pretty well. Because what you start doing too is you start widening out that heat affected zone. And that's really adjacent to, a lot of people think the weld bead as being the most critical corrosion area. It's not. It's the heat affected zone, which are 2 bands right next to that weld bead. That's usually where you see corrosion start to happen. We saw these yesterday, good welds. I'm not going to go over that again. This is an example of almost no purge. I was asked this, how does this happen? This happens a lot in place welds, like on long pipelines. You put a long pipeline up and say it's running a couple hundred feet, and you've tacked everything together, and you've done good tack welds, and then you go and you have to purge that line of all the oxygen, which means you're going to hook up an argon line, you're going to put a plug on the end with an argon hose going in. On the other end, you're going to put something to provide back pressure so you can provide some level of pressure inside that line. Now, at every one of those tack welds, you're going to leak argon out. So you've got to know how much volume of argon you need to fill that line and keep it filled, and then you got to wait till it gets filled. People get impatient. Oxygen is lighter than argon, and so it goes to the high point. And so you start welding too early, and you got, on your line up here, you got oxygen still sitting there in the top of the line because argon hasn't been moved through at a high enough velocity or had enough time to remove all the oxygen. That's usually how this happens. The other thing that happens is they just forget. That does happen. Your weld head, it's literally got a dial on it. When you turn it on, you can hear that argon hissing out of it, and that's your blanket at your weld head. And people remember that, but oftentimes that inside is just a process or procedure you got to remember. They think, oh, well, Bob did that, so I'm sure his line's purged, and Bob didn't do it because he went to lunch. And the other question that came up is, how do you fix these? You cut them out and replace them. There's no going back from this. You don't fix it. We talked about this earlier, the tack welds. Tack was too hot, penetrated the line, causes sugaring, and the welds never can consume that properly. Good tack weld. We addressed this yesterday as well, the lack of penetration. We talked about the sulfur content causing lack of penetration at times, the weld bead wanting to move off. This can happen as well. I just saw an example of this week. As you're coming around, there's what's called a tail off. Fabricator, weld technician will know what that is, but it basically is, as you're coming around, you're going to slowly tail the weld off, the pool off to get it. And you can see it, I can show it to you in what a tail off looks like, but it's kind of just the weld bead starts to narrow down and it tapers down very gradually. It usually tail off is 1/4 of an inch long, something like that. You want to have your weld bead, as you come around, you want to have it still fully intact as it overlaps the next one. If you start your tail off too quick, what can happen is on the inside, you get a small area of lack of penetration because you started to tail off too quickly before you basically got your full loop done. And this again can happen just for speed, or they're not really paying attention because they're trying to get that weld done as quickly as possible. So as your weld pool comes around, if you ever watched, it's kind of neat to watch a weld pool because it literally is just looks like a droplet of water shaking around. Any impurity that's not going to melt into that weld pool will float. And as you tail off, it just basically keeps floating until it can't go anywhere, and that's usually where it gets left. A couple of things you can do. One, be sure your end prep is done well. Those impurities can come from the inside as well. So it may be on the inside of your tubing, and it moves to the surface of that weld pool depending on where it's at in the weld pool. But cleaning the tubing up really well, making sure there's nothing there. Even the environment you're welding in. This is an interesting thing, but if you go to a fabricator's shop, almost all fabricators now have 100% stainless steel shop environments. One of the reasons is that airborne dust can make its way in. So if you've got a heavily burdened, dirty environment, the impurities in the air can make their way into that weld pool as you're welding, and it can cause that as well. So if you're having your guys weld stuff and maybe over here they're doing some sort of maintenance, it's in kind of a room, they got the door open and there's a gravel driveway and it's just dirty, you can potentially get that debris in there from that. If you can, just verify you're not seeing that on the inside of the welds, because you've had debris, so you want to be sure you don't have it on the ID. But if it's even if it's on the ID, you can remove it. On OD, yeah, you can absolutely just hit it with a grinder, remove that debris, and then let it repassivate just by cleaning it up. This is actually an example of, I don't know for certain, but my solid guess is that was probably debris that got left in the weld pool in there. It probably blew out as it was welding, is what it looks like to me. So 18.1 is tube. 18.2 is the coloration charts. D18.3 covers equipment and tanks. So a lot of equipment manufacturers around here probably have lots of people familiar with D18.3. D18.3 certainly allows for a lot more welding techniques, because there are a lot more welding techniques that are used for larger equipment, heavier, thicker wall material than what is strictly required by D18.1, which is mainly TIG welding. It also allows for different types of, you can use acid pickling, grinding and polishing, color cleaning methods for removing color from your welds. I showed the terrible little cluster of welds there yesterday. When we think about microbial harborage and what a poor weld can create, you can imagine a pit, a fold, a crack, a crevice. I think everyone can kind of see those and go, oh, yeah, stuff's going to get in there. That's not clean. That's going to be hard to clean out. But one of the things that oftentimes we don't think about is what's called MIC, or microbial induced corrosion. And I see this more and more. It used to be kind of a unique thing. You didn't see it that much. It was unique applications. But I think it's becoming more common. What microbial induced corrosion is you get a small spot that's non-cleanable, a pit, crack, a crevice, something like this. Microbes start to form in there. They actually will create a biofilm locally. They protect themselves from cleaning. And then it creates its own little kind of environment where its excrement, for lack of a better term, is oftentimes high acidic. It's going to continue to corrode and pit and create a localized corrosion, which then results in usually a blowout in the line. Sometimes, if you're lucky, you get a blowout in the line and you know it's there. Most of the time, you just end up with lots of localized corrosion that just continues to spread. And I've seen insides of like pump casings that are very thick, and they've had MIC start, and it literally started channeling underneath the surface, and then all of a sudden parts of the surface of the well or the stainless started flaking off, and now you've got patches of just awful. I mean, it literally almost looks like an ant farm started creating under the surface. This can also happen if you've got stress chloride cracking corrosion, which is where the stainless has been exposed to salts, high salt content at high temperature. You get those cracks forming, and then you can actually get MIC forming in the cracks of the chloride corrosion. All that being said, there's other things, little tiny cracks and crevices in these welds, particularly because the weld itself is more susceptible to corrosion because it's in a heat affected zone. It just creates an environment where you can have a lot of failures. What does a material failure look like? That's one. That is stainless steel. That is 316L stainless steel. The common failures for why we see that. Let's talk about some advanced techniques. These are some that I've seen. Some of them are specifically allowed and named in D18.3. But D18.3 doesn't disallow other types of techniques for welding. Obviously, we're familiar with the arc welding, laser beam welding, electron beam welding, submerged arc. Those are all listed in D18.3. Some other ones I've seen, friction welding, friction stir welding. Difference there, friction welding. So literally what it is rather than adding an electrical arc and causing heat to metal or metal to heat up, you're spinning the metal at high speed, and the friction between the metal is actually causing them to weld themselves together. Friction welding it's usually something like you're trying to weld two shafts together. You put one in the lathe, put one fixed, you start spinning at high speed, you have to finish the ends properly, and that friction actually welds the two pieces together. Stainless probably works very well for this because it tends to gall very quickly. Friction stir welding is where you actually are spinning a head on a mill, and that head is causing friction, as we kind of see here, and it's actually welding the two plates together by the heat it creates in the friction created from that head spinning. Of those three, some interesting things about that, obviously, friction stir welding, the heat affected zone on both types of friction, actually on all three of these, the heat affected zone is less. So we talked about corrosion caused by heat affected zone. We talked about that a little bit yesterday. I'll go into that maybe a little bit more in depth. When you are melting metal in any means, metal has a balance of alloys, and how for it to work, those alloys have to be dispersed homogeneously as best as possible. When you melt the metal, those different elements are separating out into their groups and then solidify at different rates, and you get things like carbide precipitation. Carbide precipitation is where the carbides literally precipitate to the surface. If you want to see a good example of this, get yourself a rare earth magnet and run it over some stainless parts, a stainless T with tri-clamp ends on it, stainless elbow with tri-clamp ends on it. The magnet will not feel like it's magnetized to anything until you get to a weld. And it's a way to tell everywhere there's been a weld, because if there's a weld there, even if it's been polished and ground and polished and removed, that magnet will pick it up because of carbide precipitation. The carbides have precipitated enough that now it's ferritic and the magnet can detect it. These different types of welding techniques do offer some advantage from the fact that they aren't creating as much heat, so you're not getting as much of a heat affected zone, which can be helpful in those types of situations. There's limitations, or else everybody would be doing it. Obviously, as far as how thick the material can be, obviously you're not going to do a lot of multi-pass welding, thick plate, and those sorts of things with the friction stir welding rather. The rotary welding, certainly limited applications. You're not going to necessarily find that used everywhere. Passivation. I think one of the biggest misnomers people have is that they think passivation is a chemical process. Chemicals work to allow the metal to passivate, but stainless naturally creates its own passive layer in the presence of oxygen if it's allowed to be exposed to oxygen. Typically, you want at least 24 hours of oxygen exposure. I even recommend 48 hours, but it needs to be dry and clean and free of any sort of debris or oils or anything. Water, yeah, anything that would keep oxygen from contacting that stainless surface. So when people do a passivation, they're usually doing some sort of a citric. We used to use nitric acid. The whole reason for that is we're trying to strip away everything from that surface so that it can be exposed to oxygen for that period of time, but it isn't something that happens in an hour. You need to have residence time for that passive layer to form. There is a study, so the 24 hours I didn't just get out of the air. There is a study that was done, I believe by somebody in Germany. They were able to measure the angstrom level of the passive layer, and that's where my information came from. And in the biopharmaceutical industry, they do address that more precisely as to what the recommendations are. I think there it's minimum of 48, but 24 is usually.
Who are we? So the Nickel Institute is the global association of the leading primary nickel producers. Our mission is to promote and support the proper use of nickel in appropriate applications. Nickel is a key element in more than 75% of all stainless steel that's produced, and 20% of all stainless steel production is used in food contact applications. So it's a very interesting application for the Nickel Institute. And these are the member companies of the Nickel Institute. Maybe you recognize some of them. They're mining companies or companies that refine the ore to produce nickel metal. Just recently, the Nickel Institute, we produced a publication for the Chinese metallurgical industry press on the application of stainless steel in food processing industry. And there's an English version and there's a Chinese version. It's about 60 pages. So if you are having any equipment produced in China and you're just wondering about the knowledge of the manufacturer they're using, you could see if they're maybe using this, but it's only available in China. You couldn't buy it here in North America. And this is just the table of contents for this publication. It covers things from food safety and hygiene, design principles, surface roughness, stainless steel selection, storage and handling, transport, and has some examples of material selection. And on the editorial committee, we had Eric Partington, who's the chairman of eHedge in the UK and Ireland. We also had a Dr. Graham Sussex, who created the Australian Stainless Steel Development Association Code of Practice. It's another publication on the fabrication of stainless steels for food applications. So we've got people from around the world who were involved in creating this publication, so it's pretty well written out. Today, the outline of my presentation is why stainless steel, avoiding corrosion, stainless steel's examples in food contact, surface finish, welding, and mechanical properties. Why stainless steel? This is really just the basic. Stainless steel is a steel that possesses a minimum chromium content of 10.5%. And in the presence of oxygen, whether it's in air or water, chromium gives the stainless steel the ability to spontaneously form a thin, invisible, protective and self-healing surface layer called a passive layer. And this is demonstrated just in this chart here, where we're looking at the chromium content in various different types of steels. So if you were to take steels of these varying chromium contents and you were, say, to hang them on a tree outside this building and then measure the corrosion rate, you're going to get a curve like this, and you're going to see that once you get down to about 10%, then it flat lines out. It doesn't matter whether it's 10% or 16%, you have a very low corrosion rate. And so that's why 10.5% is the minimum chromium content for a stainless steel. If we were to put this in a much more corrosive environment, this curve would change and it might not flat line out until 14 or 16%. But a stainless steel by definition is 10.5% chrome. A stainless steel with only 10.5% chrome, it might stain in air or water, and will definitely stain or rust when exposed to salt and mild acids. Most stainless steels contain more than the minimum chromium content. The higher the chromium content, the more corrosion resistant it'll be. NSF 51 stipulates a minimum chromium content of 16% in a food zone. And type 304, also called 18-8, which has 18% chrome and 8% nickel, for ease of fabrication. 304 and its varieties are the most produced stainless steel in the world. Other alloying elements can improve the corrosion resistance, in particularly molybdenum, which is especially useful in foods containing acids and salts. And you probably have examples of that you've seen in your own work. Type 316 with 2% molybdenum is the most common of the moly-bearing stainless steels. Some other special stainless steels contain up to 6% molybdenum. And then here is an example of some of the common stainless steels. Here's 304. As you see, it's got chrome and nickel, no molybdenum. 316, 16 to 18% chrome, 10 to 14 nickel, and 2 to 3% molybdenum. Then we have 2205, which is a duplex. It's got higher chrome and higher molybdenum, so it's more corrosion resistant than 316. And then we can have like a 6 moly superaustenitic stainless steel. In this case here, I'm showing one that's called 254 SMO. There's another one called AL6XN. It's about 20% chrome and 6% molybdenum. So we're going from least corrosion resistance to a higher corrosion resistance. Stainless steels are the metal of choice for food contact surfaces because of a combination of factors related to corrosion resistance, mechanical properties, and the ability to be fabricated and welded. Stainless steels with the proper surface finish are easily cleaned and disinfected, but it's still necessary to select the appropriate stainless steel alloy for the application, primarily for its corrosion resistance. For many food contact surface applications, type 304 is sufficient. However, for specific applications, there may be a need for stainless steel materials with special properties, either higher hardness, higher strength, or greater corrosion resistance. These individual properties can be met, but sometimes with restrictions. So there are dozens of stainless steel alloys classified into 5 major families based on microstructure. And these 5 families are the austenitic family, the nickel-bearing ones, which include things like 304, 316, Al6XN, which is one of the 6% molybdenum alloys. There are ferritic, martensitic. Martensitic you would see like used in chef knives and that. Precipitation hardenable. And duplex. Duplex has a mixed microstructure, which is approximately 50% austenite and 50% ferritic, offers higher strength and better resistances to particular types of corrosion called chloride stress corrosion cracking, which I'll mention a little bit later. And so the austenitic, duplex, and precipitation hardenable alloys, they are listed in the 3A general requirements. Here is just a table rating the various families of stainless steel, austenitic, ferritic, duplex, martensitic, pH, with regards to number of characteristics, tensile strength, formability, weldability, ductility. And we can see here under the austenitic, they're classified as excellent with regards to formability and weldability and ductility, and that's why you make food processing equipment out of it. What kind of conditions could cause corrosion issues on some stainless steel alloys? Strong acids and strong caustics, chloride salts, cleaning solutions with chlorine and hypochlorite, and high temperatures. And in the case of over 60 degrees C, with the chlorides present, you might get chloride stress corrosion cracking, but higher temperatures increase the corrosivity of an acidic solution. So the forms of corrosion, there's basically 2 general forms of corrosion. There's uniform or general corrosion, and there's localized attack. You don't see general or uniform corrosion in any food processing application because you've picked a stainless steel that's going to be resistant. But you might see issues with localized corrosion. And some of the forms of localized corrosion are pitting corrosion, crevice corrosion, stress corrosion cracking, and intergranular corrosion. So in the case of pitting corrosion, at least in a food contact application, in stainless steels, pitting corrosion is generally caused by presence of chlorides. And we have a picture here showing, say, some pits that are formed on the surface of a stainless steel, looking down on the surface. And then here's a cross-section of a pit, looking at it on a cross-section. And once pitting starts, it keeps on growing as the environment inside the pit is completely different than the general environment outside the pit, because it becomes more acidic inside the pit. In fact, you're producing hydrochloric acid inside the pit. Where do chlorides come from? Well, naturally, they're present in food, and they're there because of, say, salt added to food to improve taste. But you can also have pitting from other chlorine chemicals, being chlorine or hypochlorite in disinfecting solutions, and at much lower levels than what they could cause pitting at much lower levels than what you would see with chloride. You can rank the various stainless steels with regards to their resistance to pitting corrosion by a formula called the PREN, which looks at the chromium content and the molybdenum content and the nitrogen content. And here are the same 4 stainless steels that I had showed previously. And 304, since it only has chromium in it, has a PREN of 18. 316, which has both chrome and molybdenum, its minimum PREN based on that composition is 22.6. 2205 is 34.1, and a 6 moly stainless steel is about 42 as a PREN number. There have been a number of different formulas created for PREN. This is generally the most widely accepted. There's nothing wrong with the other ones, but this is the one that is just generally is the one that's used. And it can depend on, there's a slightly different formula for duplex, but it doesn't change the ranking. You know, if you use the duplex formula and you used it on these things, you might get slightly different numbers, but everything would be ranked still the same. It's only a number to be able to rank the steels, and we know then that a 6 moly is better than any of the other 3 above it, and that 304 is the least corrosion resistant, at least with regards to pitting corrosion. PREN is used for ranking materials. The higher the PRN, the better the pitting resistance, but it's just a means of ranking. You can't use it to determine whether a stainless steel is going to be resistant to pitting in a particular chloride environment. Here I'm just showing possible maximum chloride limits for 4 stainless steels in flowing water at about a neutral pH, at 25 degrees C with no aeration. And 304L, we would generally say, okay, it's going to be good in about 200 parts per million chloride. 316 in about 1,000 parts per million chloride. 2205, 10,000 parts per million chloride. And 6 moly up to about 20,000 parts per million chloride. And 6 moly stainless steels, because of this resistance to chloride, they're considered seawater resistant. So they have a really good resistance. And the PREN really, like I said, it only just gives you a ranking, because it doesn't help you identify whether a particular stainless steel is going to be resistant in a particular environment, because we can look here and you see the PREN for 304 is 18 and 22.5 is about double that, but it can handle about 50 times more chloride than 304L. So the PREN is just simply a means of ranking materials. If you had an instance where 304L wasn't working, and you knew that the parts per million was, say, under 1,000, well, then, yeah, maybe you look at 316. But if the chloride is more than 1,000, well, then maybe you're looking at something like 2205. These numbers here, they're just rule of thumb guidelines for flowing water at 25 degrees C with no aeration. But if you lower the pH and you make the solution more acidic, the chloride content that the stainless steel is going to be able to resist is going to be lower. And if you increase the temperature, the amount of chloride that the stainless steel can resist is going to be lower. And if it's stagnant conditions, again, the chloride content level would be lower. And if there's crevices, the chloride content would be lower. So it's not just simply to say, oh, what chloride level will a stainless steel exist? There are many, many factors that affect that. And here I've just kind of just shown another hierarchy of stainless steels. Here's the austenitics from 304, 316, 904L to 6 molys. And here we're increasing the corrosion resistance. And these are the alloys that most people would be familiar with, but there are duplex alloys now which have the same range of corrosion resistance or PREN resistance. So there are things like 2101, 2304, which is kind of equivalent to 316. 2205 is kind of equivalent to 904L. And then there are super duplex stainless steels, which are equivalent to the 6 moly super austenitic stainless steels. How does Hastelloys fit in? Well, Hastelloys are a nickel alloy. They have a higher molybdenum content than a stainless steel. And so they have greater resistance to chlorides than a stainless steel would. And really, the nickel alloys like Hastelloys, they're just on the continuum of, they're related to stainless steels because they get their corrosion resistance from chrome and molybdenum just the same as stainless steels do. They get it from chrome and molybdenum. It's just that you can't have a stainless steel with as high a chrome and molybdenum as a nickel alloy because bad things happen to the microstructure. So you have to have more nickel in it, and more nickel allows you to have a steel or a nickel alloy that has more chrome and molybdenum and therefore has a greater corrosion resistance than a stainless steel. Here's a picture of a Type 303 stainless steel used as a plug in a tomato paste processing plant. It doesn't look pretty. And in this case, a duplex or possibly a 6 moly might have been preferred to be used because tomato paste is acidic and has chlorides in it. And part of the reason why 303 didn't work very well is it's a high sulfur free machining stainless steel. So it has a lot of sulfur in it, which reduces the corrosion resistance. The sulfur creates a lot of sulfide inclusions in the material, which are sites for pitting corrosion. So if you've got any chloride present, the chloride is going to attack where the sulfide inclusions are. So 303, even though it has the same chrome and nickel content as 304, it's just not as good because of all the sulfur in it. Crevice corrosion. We don't often see crevice corrosion in the food industry because you're trying to eliminate any kind of crevices because the crevice is where it's going to harbor bacteria. But however, flange faces could be one place where you might see crevice corrosion because you've got a crevice between the gasket and the flange face. Then there's stress corrosion cracking, which is another localized corrosion. And in this case, it looks like the material has become brittle because you get very specific localized cracking due to the presence of chloride and temperatures. So In the food industry, if you were to see chloride stress corrosion cracking, which is a multi-branched crack, you'll only usually see it because it's related to chloride that's present in the environment, and typically you need a minimum temperature of 60 degrees C to see chloride stress corrosion cracking. With regards to stress corrosion cracking, 304 and 316 are quite susceptible to chloride stress corrosion cracking. 2205 is better than 316. 6 moly grades are better than 2205. And C-type family, the C family of nickel alloys, which are like the Hastelloys, which the other fellow was asking about, are virtually immune to chloride stress corrosion cracking. And we can see here, the PREN gives us a clue here because as the PREN goes up, resistance to chloride stress corrosion cracking increases. Some examples of material selection. Milk is not a particularly corrosive food product. It can be handled by stainless steel with even lower chromium content than in 304. However, 304 is the minimum to be able to withstand the cleaning and disinfection chemicals, which are much more aggressive or corrosive than the milk itself. In some cases, cleaning might be done with sodium hypochlorite in low dosages, but care has to be taken because sodium hypochlorite is an extremely strong pitting agent. And if you leave it in contact for too long, you could cause pitting corrosion of the 304 stainless steel. And that's types 304 and 316L are most commonly used grades in the dairy industry. Like it's the case of, say, like tankers, 304L could be used, but 316L might be used in butter production because butter can have a lot of salt added to it. Here's some specific examples. A dairy was experiencing corrosion in a process for salting of cheese. The brine used to do the salting contained 30% sodium chloride and had a pH of about 5.3. Even though the temperature was low, it was only 10 degrees C, they needed a 6% superaustenitic stainless steel to prevent pitting in the equipment used for the salting of the cheese. An ice cream manufacturer had problems with pitting and stress corrosion cracking in ice cream molds made of type 316. The corrosion was caused by the use of calcium chloride as the refrigerant in combination with heating by steam, which is used to empty the molds. The corrosion problem disappeared by switching to 6% molybdenum stainless steel. But in this case, the corrosion wasn't caused by the ice cream, it was caused by the chloride solution that's used as a refrigerant. So this is a case where it's the process that dictates what stainless steel needs to be used. And then say in the production of sugar within the sugar industry, some sugar solutions can contain up to 10,000 parts per million of chloride and a pH of 5. And sometimes this solution is at 80 degrees C and can cause chloride stress corrosion cracking of type 316. But when duplex stainless steel type 2205 has been used to manufacture these tanks, they've been in service for 10 years and there's been no problems. Pork meat jelly and vegetable jelly, and this is another example of where there's a lot of chlorides present in the production of these foods. And the laboratory corrosion test was performed to evaluate the materials for equipment to heat pork meat jelly and vegetable jelly. And type 316L exhibited corrosion attack. But then steels with higher PRENs like 904L, 6 moly superaustenitic, 4565, which is another type of superaustenitic, duplex 2205, 2507 is a super duplex stainless steel. They were all crevice tested for 31 days at a temperature of 95 degrees. And 904L and 2205 showed shallow pits on cut edges, while the 6 moly, the 4565 and 2507 showed no corrosion. And that's because in the previous table I showed you that 904L and 2205 have about the same PREN number, which is about 34 to 35. These other alloys, the 6 moly, the 4565 and 2507, they have a PREN that's greater than 40, probably somewhere between 40 and 42, and they're resistant to the salt in this application. In the brewery industry, stainless steel is the primary material within the brewery industry. Normally type 304 is sufficient, even though the process vessel and the piping systems are operated at up to the boiling point. And normally brewing water is sufficiently low in chlorides that 304 should not have a problem. I had said before that you could have up to about 200 parts per million of chloride in 304. In typical drinking water, at least here in North America, a lot of places, it's only like 20 parts per million. So if you're using that to brew your beer, there shouldn't be a problem. But often there are sections that are above 60 degrees C, and there can be a risk of chloride stress corrosion cracking because there can be parts of the brewery equipment that have insulation material on it, and insulation can have chlorides in it. And if the insulation gets wet, the chlorides will leach out and then will come up against the stainless steel. And with repeated cycling of wet and dry, the chlorides can concentrate and at the metal surface, and then you could get chloride stress corrosion cracking, so you would need a higher grade of stainless steel because of things happening on the outside. And for carbonated soft drinks, generally type 304 is generally sufficient for processing and bottling carbonated beverages, even though the carbonated beverages have carbonic acid in and phosphoric acid. At the concentrations that they're in a carbonated beverage are not a problem. But here's an instance in Perth, Australia. Type 316L is used because their water has a relatively high chloride content in it, and so they have to use 316L rather than 304. So now for a quiz. So which of these four products needs the highest alloyed stainless steel? Coca-Cola, which is acidic, milk being pasteurized, ketchup being pasteurized, salted butter being melted. It's the ketchup, because ketchup is both acidic and contains salt, chlorides, and is very corrosive, therefore they're at high temperatures. Because like the pH of the tomato is in the 4 range, and ketchup, I guesstimate it has about 5,000 parts per million chloride. I estimated that by looking at the dietary information on the ketchup, how much sodium was present, and then I know there has to be an equal amount of chloride present, so you get about 5,000 ppm of chloride. As a side note, most stainless steels are resistant to organic acids like acetic, citric, lactic, oxalic, and malic, present in food or used in food processing at concentrations and temperatures used in the food processing industry. But in this case, if you add chlorides to it and you put it at a high temperature, it becomes a problem. Surface finish. Probably the most important feature of food contact material from a cleanability point of view is the surface finish, with microorganisms only about 1 or 2 microns long and in relation to a human hair, which is about 100 micrometers in diameter. So we can see there's a bacteria and a hair. And so also with surface finish, as you would all know, EHEDGE and 3A require surface finishes with RA values of no more than 32 microinches or 0.8 micrometers for food contact. But even at that surface finish, the bacteria can still hide in the troughs. They're still small enough to hide in the troughs. But the reason that it's acceptable for food processing is that a 2B surface, which is typically in a surface finish range, can be cleaned easily after every use. Cold rolled stainless steel sheet with a commercial 2B finish would have a RA value of around 16 microinch, about half of what's required by 3A and EHEDGE. And being hard and corrosion resistant material, it will usually retain this smoothness for life. Just to point out, a polished finish may be rougher than a mill finish. So we can talk about a number 4 polish. I don't know how common number 4 polish is in the United States. It's very common in Canada. I think in the United States, a lot of times they use maybe a number 3 or something like that, but it's still number 4? Okay, it was number 4, okay. But you produce number 4 by polishing 2B, which is a cold rolled finish. And the range for cold rolled finishes is from here to here. But when you polish number 4, in fact, you can make it rougher than what it was a cold rolled 2B. But even still, here, the maximum we're showing here is like about 25 microinches, which is less than the 32 that's required by EHEDGE and 3A. The common ASTM designations for stainless steel surfaces, such as number 4, they specify a process to achieve a finish and not the attributes of the surface itself. And the result can fall out of the desired surface roughness range. Euronorm finishes in the 1000 or 10,088 provide a larger number of specifications than ASTM A40, and some require particular RA values. So like when we talk about a 2B finish or a number 4, there's no surface roughness measurement that's required to certify it to those surface finishes. That's all defined by 3A. And although the measurements involved are microscopic, research indicates there is significantly higher resistance to corrosion in stainless steel surfaces with a roughness below 5 micrometers or 20 microinches. And that's shown in this graph. This was developed by the International Dairy Federation and reported in Bulletin 189. And this is just showing surface roughness in micrometers along the bottom. And then this is just kind of a relative corrosion rate. It's not an actual value, it's just relative. And we're looking here where some 316 material was exposed. And I don't know what the solution was, because this was an old study. And it was immersed for 8 minutes, which is B, or 14 minutes, which is A. And we can see the corrosion rate increases quite slowly until you get to about 0.5 micrometers. And then it starts to increase rapidly after that. And the 3A and E hedge surface finish values are here at 32 microinches or 0.8 micrometers. And so once you get beyond that, the corrosion rate on your stainless steel would increase. This is what a 2B finish would look like, magnified, and this is a number 4 that would be polished from a 2B, and then what the surface could look like after electropolishing. Heat tint from welding. Heat tint is a term used to describe the colored surface oxides that form in weld areas resulting from the heat of welding. Another term sometimes used is just weld discoloration, and it's caused by a reaction with oxygen or moisture. And heat tint is of a concern as it reduces the corrosion resistance of the weld. The weld becomes very susceptible to chloride stress corrosion cracking, partly because of the presence of these high temperature oxides that are formed during the welding process. And also underneath that, there's a thing called the chromium depleted layer. So this needs to be removed to ensure that you have optimum corrosion resistance in the weld area. Yeah, so heat tint is of greatest concern in stainless steel tube and pipe welds where its removal is difficult or impossible. And just to show how heat tint and surface finish can have an effect on corrosion resistance, this here is what we call a CPT, which is a critical pitting temperature. So in this case, we're testing 2205 in a 3% sodium chloride solution. And it's tested in that solution, and the temperature is brought up until the material basically starts to pit. And so in this solution, 2205, when it comes from the mill, could have a critical pitting temperature of 60. It's not going to pit until it gets to 60 degrees C. But if you weld it and you leave the heat tint on it, it'll start pitting at about 30 degrees C. You can almost restore that back to the original by pickling it, and you can also improve the pitting resistance by grinding or stainless steel brush or blasting, but this wouldn't be allowed in a food application because you're going to have a surface finish that's greater than the 32 microinches allowed. And now with regards to welding of stainless steel, and this with regards to like L grade. L means low carbon, and it's necessary to have low carbon when welding to maintain corrosion resistance in the weld area. But there is the non-L grade, which has a higher carbon content, because carbon gives it strength. But there is a dual grade, which is like 304, 304L or 316L, and it's a product that's certified to meet both the requirements. It has the low carbon of the L, but it meets the minimum strength of the non-L because a little bit of nitrogen is added in place of the carbon to maintain the strength level. And so we can see here, 304, 316 has a max 0.8 carbon. This is the yield and tensile strengths. For 304L, that's the max, and this is the minimum yield and tensile strength. But you notice that with 304, 316, there's no minimum carbon, there's just a maximum carbon. So you can produce a dual certified material which meets the O3 max and the L grade, but by the addition of a small amount of nitrogen, you get the yield strength of the non-L grade material. And why do we talk about L grade versus non-L grade? And that's because there's the process of sensitization. When you're welding, if the carbon content is greater than O3, chromium starts to get tied up with carbon to form chromium carbides at the grain boundaries, which reduces the amount of chromium content along the grain boundaries. So now you've got less chromium, you have less corrosion resistance along the grain boundaries. But you might only be knocking down the chromium, like this, we could say this is like maybe a 304, so we've got like 19% chromium, and it may be in a worst case scenario, the chromium at the grain boundary is down to like 13. It's still a stainless steel. And in a mild environment, say, I could say like in milk, you're not going to get corrosion along the grain boundaries with 13% chrome. It's enough. But if you were using it, and we had the example of, say, like the ketchup, and you had welded a 304 with or even a 316 with the higher carbon, you could reduce the corrosion resistance along the grain boundary enough that you could see intergranular corrosion in the heat-affected zone of the weld. So intergranular corrosion, it's caused by the difference in corrosion resistance between grain boundaries on the matrix, caused by grain boundary precipitates of chromium carbide that form during the welding process, and therefore then you can start to see corrosion around the various grains and it kind of falling out. But this doesn't happen anymore because that's why L grades were created. And L grades have been around since the 80s. And probably most of the equipment that's been created since the late 80s, even though you might have a test certificate that says that it's 304, it's probably L grade. Because when they first started to create L grade material, people had a hard time understanding how you could have something that was dual certified. How could it be 304L and just 304 at the same time? So, because I worked at the metal distribution industry, and we would have two certificates, one that said it was L grade and another one that said it 304. And depending on what the customer ordered, that's the certificate we would give them. But then eventually people got used to it, and in the ASME pressure vessel code, they actually had to write it into the code that says material that is dual certified as 304, 304L is acceptable as either single grade. So you don't see problems with intergranular corrosion because in the last 40, 45 years, everything, at least plate and even pipe, anything that's going to be welded will have had a low carbon content in it. The only time you see any with a high carbon is maybe in some round bar, because you're usually not welding it, you're making a shaft or something like that. And one final little thing I'm just going to mention here is about sulfur control for automatic welding. In the ASME bioprocessing equipment, it has established a sulfur control limit of 0.5 to 0.17 on stainless steel tubes to be welded to ensure uniform weld penetration. This is important when you're doing orbital welding of a pipe, because sulfur is considered a surface active element, and if the sulfur is too low, you don't get proper weld penetration, so you could be orbital welding and you don't get full penetration of your weld. So for orbital welding, it's specified that the sulfur needs to be in this range, because the stainless steel industry doesn't like sulfur to be present, because that means you have sulfide inclusions. Sulfide inclusions are places that can be sites for premature pitting corrosion on a stainless steel. So they've done everything they possibly can to get the sulfur out of a stainless steel. So generally it's less than 0.001. But then when people started to do orbital welding, they found that they had a problem. And so they had to increase the sulfur content. And we can just see this in this diagram here. With a higher sulfur content, it affects the circulation of the weld metal in the weld pool, so you get better penetration. And if you have a low sulfur, it doesn't go as deep. So it's just an interesting side note. And the final thing here is just to show mechanical properties. I've mentioned duplex stainless steels. And also you had asked before about the mechanical properties on Hastelloy. So you can see with an austenitic stainless steel, the minimum yield is 30, minimum tensile 75. Super austenitic stainless steel, which has in fact some nitrogen in it, has a yield strength of about 45 and a tensile of 95. Duplex has a yield strength of 65 and 95 for the tensile. So it's double the yield strength in comparison to an austenitic stainless steel or a 304. So you can build equipment. You might be able to use thinner material to achieve a lighter fabrication, maybe reduce the cost a bit. And then you had asked about the Hastelloy. So here's nickel alloy C276, eventually Hastelloy C276. The yield strength is 41 and the minimum tensile is 100. It's just a real mishmash of alloying elements, chrome and nickel and molybdenum, and so it's just solid solution strengthening, and so it's a bit higher than an austenitic stainless steel. We've got a lot of information on our website about stainless steel applications and fabrication. We have a LinkedIn site where we publish a number of different articles, I think almost on a weekly basis, and we have our free technical help available. Just go to our website. You click the yellow button, technical help, create an account, post your question. I see it first. I might answer it, Or if it's much more complicated, then I send it to one of our other dozen consultants, and you got a question, anything, welding, fabrication, whatever, we'll respond to it. Thank you very much for your attention.